Welcome to Group Theory, Step by Step. In this first video, we'll learn about the groups of order -6.
That just says 1 through 7. Not everything is an equation.
Ah, yes, the groups of order 1 through 7. Group theory is an area of math, and there are many areas of math. Geometry is all about position. Calculus is all about change. Set theory is all about being annoying. And groups are part of algebra, which is all about operation, the way that things combine. So a group is a bunch of things called elements, and some operation that combines them. For example, we could have the integers, which combine using addition. So the smallest group has just one element.
Should it still be called a group if there's only one element?
Sure, like a party is a group of people, and then awkwardly sitting outside is me, a group of person.
That's because you only ever talk about math.
Oh, speaking of math, the operation can be to multiply. 1 times 1 equals 1. Or we could use 0. 0 times 0 equals 0. And we could switch the operation to addition. This is also a group.
But we couldn't use addition with 1?
Exactly. 1 plus 1 should be 2, but 2 is not an element of this group. We could use exponents though. 1 to the 1 is 1. And all of these examples are groups of order 1. The order is the number of elements. But here's the thing. There is only one group of order 1. These groups are all equal. But we use a squiggly equal, and we say they are isomorphic, which means that the concept of the groups are different, but they act the same. They all just have thing, and thing mixed with thing equals thing. And this is the beauty of group theory. If we take any integer to the 7th power, then subtract itself, we get a multiple of 7. This may seem weird. There's no clear reason why.
There's also no clear reason why you brought this up.
It's an example of group theory. The group of multiplication mod 7 is isomorphic to the rotations of a hexagon. But a hexagon is easier to think about. Let's mark the top corner. If we do any rotation 6 times, that mark returns to the top. 6 rotations equals 0 rotations. And that means that 7 rotations equals 1 rotation. Now remember the isomorphism. These groups are the same, so this equation becomes x to the 7 equals x to the 1, plus a multiple of 7, since we're in mod 7. Then we subtract x from each side, and there's our equation. For any integer, x to the 7 minus x is a multiple of 7. Group theory allows us to take a problem from a difficult group and solve it within an easier group. Now, let's take a look at some groups of order 2. We could have 1 and -1 and multiply them. We get these equations. And equations are nice, but a multiplication table is even cleaner. This table shows the elements and the operation. It fully describes the group. For another group, we could have the even and odd integers using addition. This is a group. Or we could have 0 degree and 180 degree rotations. How about true and false, and combine by comparing?
Combine by comparing?
Yeah, true equals false, that's false. But false equals false, that's true. And it turns out, these groups are all isomorphic. If we just look at the color of the tables, we see they're identical. There is only one group of order 2, just like order 1.
What if we have 1 and 0 and then multiply them? This has different colors.
Not a group.
What?
Not a group.
Why not?
Doesn't follow the terms and conditions.
There are terms and conditions?
Yeah, because groups are useful for algebra, which often uses equations like this one. And to solve an equation, it's nice to rearrange things. But in order to rearrange, each element needs an inverse. To move the 4, we have to add the inverse of 4 to each side. And the whole point of an inverse is that it makes things disappear. 4 plus -4 is just 0, which is the neutral element. It disappears if we add it to something else. So the terms and conditions are that a group must have a neutral element, and all elements have an inverse. Otherwise, algebra would be much harder. But wait, we have to be able to apply the inverse. This wouldn't work with exponents since they're not associative. These two combine first, and we can't just rearrange the parentheses since that changes the value. So we also have associativity as a term and condition.
Okay, so multiplication is associative, and there is the neutral 0 here.
Yes, but actually 1 is the neutral element since we're using multiplication. 1 disappears when you multiply, not 0.
So then this fails because of the inverses. 0 has no inverse.
Exactly. There is no a that multiplies with 0 to get 1, since that would mean that we divide by 0, and I don't want to reinvent the wheel. So this is not a group. But how did we know that this one is the only group of order 2? Well, let's start with a blank table. We need a neutral element, which mathematicians usually call e.
Why E?
Einheit!
What?
And then we have a second element. Let's just call it a. E is neutral, so we can automatically fill out these 3 cells of the table. And then there's just one left. A must have an inverse, so A times A inverse is E, which means that E has to appear in the A row. So it'll be that open spot, and the table is full. This is the only possible group of order 2.
Ugh, this feels like Sudoku.
I know, isn't it great? A group's tables will follow that Sudoku rule.
Ugh.
Each element appears once in every row and column. If A appears in the B row, that means that B times some C equals A. But we can just solve for C, meaning that this will work for any A and B. Every element appears in every row. And the same goes for columns. So now let's do the groups of order 3. We'll set up a table with Einheit and then some A and B. We can fill these out since E is neutral. Then we have an A in these 2 rows and these 2 columns. So that leaves this open spot as the third A. And similarly, we can find the third B. Then the other empty cells must be E. It's all filled out. This is the only group of order 3.
Is it always just going to be one group for each order?
No, things get more interesting soon. But first, let's take a closer look at this group. We can rename these elements to be a 0 degree, 120 degree, and 240 degree rotation. These rotations make a cycle, so this is called a cyclic group, and we write it as C3. We already saw C2 and C1. These are the smallest groups.
So then if we used 90-degree rotations, that's C4?
Exactly, and we can do this for any integer. Remember the group of rotations of a hexagon?
That was C6.
Yes, it has 60 degree, 120 degree, 180 degree, 240 degree. The naming gets kind of annoying.
It's not just the naming.
What do you mean?
Nothing. Keep going.
So for quicker naming, we usually just write this as 0 through 5, and then say that 6 equals 0. It's addition mod 6. So here is a more typical C1, 2, and 3. And now we have a head start when we look at the groups of order 4. We already know about C4, but it's not the only one. Let's Sudoku the table. E does its magic, but now what? There's a bunch of empty space.
Maybe we could...
We'll use a clever trick.
Okay.
Let's think about the inverses. E is its own inverse, but what about the others? Maybe A and C make a pair, being each other's inverse. So then we must have a loner B, which has to be its own inverse.
Why can't it also pair up?
Good question.
Bad answer.
Well, if B and C both match with A, we get that B equals C. Each element has exactly one inverse. So we get the pair, and then the 2 loners. We could use a different pair, but that would just be isomorphic, since we can just rename the elements. The only truly different group would have no pairs. Everything has a loner. So there are these 2 options. Let's start with the pair. A and C are inverses, so E must go here and here. And then B is its own inverse, so E goes here. From there, we can fill the rest in. And if we rename the elements, we see this group is C4. 0 and 2 are their own inverses, and then 1 and 3 are a pair.
So what about the other group?
Here, everything is its own inverse, meaning that the diagonal is all E, since they're squares.
The whole grid is squares.
No, I mean like square numbers.
E is a letter, not a number.
Anyway, everything else just follows from there. This group is the symmetries of a rectangle. We can rotate, flip vertically, or flip horizontally. And then, of course, Einheit is just no movement. Any move cancels itself out, and they interact. A vertical flip, then a horizontal flip, equals a rotation.
So what's this group called? R for rectangle?
It's called V.
V?
Viergruppe! So here's a summary of the groups so far. Now let's look at the groups of order 5. We have C5.
Okay, and?
Oh, that's it. It's just C5.
Well, this is your video. You have to talk.
Fine. C5 is the only group of order 5, and that's because 5 is prime. We saw the same thing with C2 and C3. They were the only groups of their order, and the same thing goes for 7, 11, 13, 17,
Calm
19.
down.
Right. For prime orders, we get just a cyclic group. But I think I'll wait and explain the reason when we get to order 7.
Why not just do it now?
The video needs a climax. We can't just end like, finally, order 7. It's prime, so we just have C7.
Seriously?
Well, the explanation will also make more sense after we've seen the triangle group, which has order 6. An equilateral triangle has 6 symmetries. There's Einheit, a rotation, 2 rotations, then there's a flip, flip then rotation, and flip then 2 rotations.
Wouldn't that be 2 rotations, then a flip?
In group theory, we read right to left.
That's confusing.
Yes, but it's because these are like functions. In a longer form, we take a triangle, first apply a flip, then apply a rotation to that, and then apply another rotation. The functions are ordered right to left, but we usually shorten it and write like this. And the order of the elements is important. It's not the same if we do the flip last. Rotate twice, then flip, equals flip, then rotate once. The elements don't commute. And that means that the table is not symmetrical along the diagonal. All the groups we've seen so far had this symmetry, since xy always equals yx for any x and y. These commutative groups are called abelian, after Abel, who studied them. The triangle group is the smallest non-abelian group. It's called D6, the dihedral group of order 6. And there's a whole family of dihedral groups. D8 is the symmetries of a square. D10 is the symmetries of a regular pentagon. D12 is the symmetries of a... You're supposed to say regular hexagon.
This is a math video, not Dora.
Yeah, okay. Anyway, looking at the table of D6, we see these colorful regions where the triangle is flipped, and dark regions where it's not flipped. And these regions form their own table, which is the group C2, using flip and no flip. In this group, we only care about the flippiness of the triangle. We're ignoring the rotations. And that's the essence, ignoring rotations. This large neutral element is made of the rotation subgroup. It's a group within D6 that we get by just repeating rotations. So, to ignore the rotations, we just say that the rotation subgroup as a whole is neutral. So in this way, D6 is the product of the rotation subgroup and C2. Except we put a little extra bar here. You'll find out why in a future video. If we use C6, which is the other group of order 6, we can rearrange the table and take the 3 subgroup as being neutral. This takes us from C6 into C3. So C6 is the product of the 3 subgroup and C3. But now let's notice, we have a group of order 6 as the product of an order 2 and an order 3. And this makes sense since 6 is 2 times 3. And earlier we had something very similar. And we could do the same thing with the Viergruppe! Setting the rotation subgroup as neutral makes C2. We have order 4 as the product of order 2 and order 2. The order of a subgroup divides the order of the group. And this fact will help us with the groups of order 7. Let's say we have some element A. What is the order of the A subgroup? It divides 7, so it's either 1 or 7. But the thing is, a subgroup is a group, meaning that it must follow the terms and conditions. It has to contain the neutral E. But it also contains A, So the order can't be 1, it must be 7. The A subgroup is the whole group. So we can just write the elements as the powers of A, meaning that this is a cyclic group. It's C7. And the same reasoning applies to any prime number. Pretty cool, right? Hey, are you asleep?
What? No, I'm awake.
You missed the most interesting part.
Yeah, I'm sure it was really interesting.
Well, that was the groups of order 1 through 7. Thanks to my supporters on Ko-fi, and join us next time to continue with the groups of order 8, then the groups of order 9, then the groups of order 10, then the groups of order 11, then the groups of order 12, then the groups of order 13.